Alright, our test is going to be very similar to our homework. So let's go over the homework. The only thing you will be given for the test is a standard periodic table of elements. Everything else you will have to memorize. So what is the correct order for the orbitals? You can memorize how to generate it. So 1, 2, 3, 4, 5, 6, 7. And these are all S's. S comes first. And then we have 2, 3, 4, 5, 6, 7. So it goes S, then P, then D, then F. So these will be our P's. Then we have 3, 4, 5, 6, 7. These will be our D's. And then we have 4, 5. And these will be our F's. You could continue it up, but no element has 6F or 7F. It doesn't matter. Or diagonals will be the correct order. So 2P's and 3F's, then 3P and 4S, then 3D, 4P, 5S, then 4D, 5P, 6S, then 4F, 5D, 6P, 7S, and then lastly is your 5F, 6D, and 7P. And you can stop there because that's the final order. Nothing is past 7P. I don't think anything actually is on. 1, 2, 3, 4, 5, 6, 7, yeah. Even look. So this is your P block section. We have 2P, 3P, 4P, 5P, 6P, and right here will be your 7Ps. Notice they're missing. This periodic table is slightly out of date. We have made some of these elements. These elements right here are all man-made. They do not exist in nature. We physically make them. So the correct order, once you know how to do this, or correct order, is 1S. There will be 2 here. And technically you can write 1S2 if you're filling these in. 2S2 for the 2 electrons here. I didn't count off if you didn't put the numbers here or the arrows because it's only asking you for the SPDF and the levels. Next will be 2P. So we fill ups first, then downs, giving us 6 in total. Next is 3S. So I have it up and down, making it 2. Then 3P, ups first, then downs, giving us 6 in total. Then we have 4S with an up and down. Then this would be 3D. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You should memorize that there are, we're just looking at electrons, there are 2 in S, 6 in P, 10 in D, and 14 in F. There is 1 S orbital, 3 orbitals for P, and so the odd numbers. So these are the orbitals, or blocks. In this diagram, there is 1, 2, 3, 4, 5 squares. When they get the electrons, you just multiply by 2. Here's yeah. And the next one after 3D is 4P. And let's make this one have only 1. So if it only had 1, the one that comes after 4P is 5S. Then I put a 1 here. If there was a second arrow, it would have a 2. So right now it only has 1. Add another arrow, this becomes a 2. This is counting how many electrons are in this whole block. So how many electrons can go in 1s? 2. For 3p, you don't really need to know the number. It's just how many can go in all the p's. That'd be 6 per level. For 5d, 10. And for 5f, 14. So determine which element is represented by the following orbital diagrams. So let's begin by just writing the energy levels and the sublevels. So this is 1s, 2s, 2p. After 2p becomes 3s, and this would be 3p. I should have told you this. This would have been helpful. We know that one block by itself will be S's. So we could have just put S for all these single blocks. And it has 3 blocks. Well, we know that p orbitals have 3. So I could have labeled all these p. And then figure out the numbers, you would still have to do this. So it should be 1s, then 2s, then 2p, 3s, and 3p. Regardless, you get the same result. Just as long as you get the numbers. And the superscripts will be how many arrows you got. We have 2 electrons there. Each arrow represents an electron. And electrons come in 2 different flavors. Either spin up or spin down. So we have 2 electrons here. We have 6 here. We have 2 here. And we have 1, 2, 3, 4 here. And it asks you to also do the element. So 2 ways of figuring out the element. I highly recommend you actually count them all up to make sure you get it right. Actually, I recommend you do both ways. How many electrons do we have in total? 2, 2, and 6 make up 10. So 10, 12, 12 plus 4 is 16. So we have 16 electrons. 16 electrons corresponds to sulfur. Once you do this method, I highly recommend you do the other one to check your answer. The other method is looking at the last one, 3p4. So these are your p blocks, and it's going to be third energy level. So this is 2p and 3p, and it's number 4. So 1, 2, 3, 4 corresponds to sulfur. So in the p blocks, we do third row, which it starts with second row here, third row here, and then fourth spot is sulfur. So if I were to draw out, we have our p blocks. The first one is boron, this corresponds to your 2p, your 3p, and this would be your P1, your P2, your P3, and your P4. So this block right here is 3P4. So going 2P, 3P right here, looking at it, this is 3P4. I highly recommend you start with counting up the electrons and figuring out this, and then you check yourself. This should be your P1s, your P2s, your P3s, and your P4s. So everything in this row ends in P4, or column. Everything in this column ends in P4, and sulfur is in that, so that means it's more likely right. It's very easy when adding up a lot of numbers to get it wrong. So let's do this one again. I know that these are S's. You can even come over here and start on the next one. I know that these are going to be my P's. This has 5, so that has to be a D. And then my order is 1S, 2S, 2P, 3S, 3P, 4S, 3D, and double checking, after 3D is 4P. And then we count 2, 2, 6. I know it's going to be the maximum number until the very end. 2, 6, 2, 10. Then check 1, 2, 3, 4, 5, 6. 6 here. So since everything is full, I know it's going to be on the it's going to be a noble gas. We can still add these up. 10, 20, 30, 36. 36 corresponds to krypton. So Kr. I can also check, again, 2P, 3P, 4P, and the sixth one, 1, 2, 3, 4, 5, 6. These all end in P6, so it is krypton. So that would be my answer for that. This would be P, 1, 2, and 2. 2 there, 2 there, 1, 2, and 3. That's 3. So 1, 2, 3, 4. 4 plus 3 is 7. So looking for 7 electrons. Our atomic number 7 corresponds to nitrogen. Double check again. This column is P1, P2, and P3. Nitrogen ends with a P3, and this first row is all 2P, so 2P3. And that is the last one right here. So let's do rules for orbital notation. Let's find mistakes. So off-ball, define your order. Hundral tells you the order you put in, the order of energy levels. Order of electrons. This is your maximum spin. Maximize same spin, so spin up first. And Pauli exclusion, at most 1 spin up and 1 spin down per orbital. So let's look at and see if we can find mistakes. This right here, we cannot do up and down here because we have spots we can put more ups. So this is the mistake. This is hundral. We should fill all spin ups first. So this should be removed, and we should put an up here. Looking at this one, again, there's two ways you could have looked at the mistake. I think most of everyone got this. This right here is the mistake. This is off-ball's rule. Off-ball says we need to fill 3s. So off-ball says fill 3s before 3p. So this electron and this electron should have went here before we started on the 3p. This one right here is Pauli exclusion. Pauli exclusion says we cannot have two spin-ups in the same orbital. We cannot have two spin-ups in same orbital. So this really should have been a down. This is another way of representing it in higher. Usually you can plot this in an axis. So this x-axis would be your orbitals, and your y-axis will be energy. And we get a nice height to them. But anyway, looking at this, we see right here, Pauli exclusion violation. Again, for the exact same reason, we cannot have two spin-ups. So looking at this, let's see, everything looks to be in order. Let's see, the arrows all look to be in order. Let's see if the 1s, 2s, 2p, then 3s, then 3p. Oops! There's a mistake right here. Now you could have done it differently. You could have circled 3D. That is the mistake. It didn't really matter as long as you indicated it somehow. If you circled 3D, I got it right. But we should have had a 4s. This is off-ball. Off-ball says 4s before 3D. Here, we have a hundredal violation. We should fill a maximized spin. We could have also circled this one right here. We should have put an up before we started doing the downs. That would give us 3 ups to 1 down. We maximize the same spin. So at most 3 ups and 3 downs can go in here. To maximize the same spin, we put 3 ups and 1 down versus 2 ups and 2 downs. Make sense? Let's go on to the next one. I think everyone did this right. So 1s2, hopefully y'all didn't cheat. I think y'all did. The reason why is online calculators do it in the wrong order, but I didn't care enough to comment on it. You copied it off the internet, they'll switch it around. And it's very obvious to me that that is not the way I taught it. There's no reason for you to switch it around. But doing RB, so you have this memorized, your 1s, your 2s, your 2p, your 3s, your 3p, and rubidium is right here, so it go 4s, then 3d, then 4p, and then 5s1. Or you can use this and just know that 1, 2, 3, 4, 5 is the 5th S. I'm going to stop at the 5th S. So I'm going to stop right here and just copy that down. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and I know the only one that's not going to be full is the last one. So for S's, can have most 2, for P's, 6, S2, P's, 6, S2, D can have 10, P can have 6, and now look at its position. Position is the first one in the S block. I'll just put a 1 right here. Double check by adding these up, and you'll see that they equal 37. So up to 3D10 is 30. 30 plus 6 plus 1 is 37. Doing the noble gas configuration, we look at the previous noble gas before it. So rubidium is right here. So we're going to go up this row all the way down to the last one, which is krypton. So I'll begin with krypton. And then it will be 5s1. I just read off that whole row. So for neon, it might be better to start off with the noble gas configuration. So for neon, previous noble gas on the previous row, so the first row is just hydrogen and helium. This is the last one. So I know this is going to start with helium. And I'll read off the entire row. 2s2 and 2p6. So 2s2 and 2p6. So I know my last one is going to be 2p6. So when writing the order is 1s, 2s, and then 2p. 2 in here, and it's in the last column, so it's going to be 6 here. Let's skip, as this is wasting a lot of time. Make sure I'll cover everything. So here, again, writing off the correct order, 1s, 2s, 2p, 3s, 3p, then 4s, then 3d, then 4p, then 5s, 4d, and 5p. This is the iodine. Iodine, I know, is 2, 3, 4, 5, 5p, and 1, 2, 3, 4, 5. So it'll be 5p5. There's going to be 5. The rest of them are going to be all full. So 2 for S, 2 for all the S's. For the P's are all going to be 6. And D for all the 10s. Noble gas configuration. We go up, krypton. And then we read off the row in order. So we have 1, 2, 3, 4, 5. So we have 5s2. And then this one starts with 3, so 3, 4, so 4 d10. And then this would be 2, 3, 4, 5, so 5 d5. Use the online calculator. They usually put the 4d10 before the 5s2. The reason for that is even though off-ball tells you this is the final order, it's technically wrong. The 4d10 is actually indeed filled before the 5s2. However, off-ball is only for figuring out the final state rather than actually telling you what's actually going on internally. So list the element for the following configurations. This is simple. We just add up all these numbers. So 10 versus 3, 2 and 4, so that's 6 plus 10, that's 16. 16 corresponds to sulfur. You could also just look. So this is 1, 2, 3, 4, 5, 6, 7. This row right here begins at 3, so 3, 4, 5, 6. This row begins with 2, so 2, 3, 4, 5, 6, and I'll even label it. This is the P's. These are the D's. And these are the S's. Highly recommend when you first get this periodic table, you do this. So 5s1, terbidium. And it corresponds to 37. You can count these up. So it's 30 to d10. Then it's up to here is 30. And it's 6 and 1 is 37. Krypton, and then 5p3. So 5 and 1, 2, 3. This would be 5p3. So SB for antimony. 5d6. So yeah, 5d6. So 5d, 1, 2, or 1. I probably should have. Actually, now I'm thinking about it. I should have put the here. So 3D. So 5d6. 1, 2, 3, 4, 5, 6. Osmium. You can also calculate it from the fact that xenon has 54. 54 plus, so 6 and 14 is 20. And then 2, so it's 54 plus 20 plus 2, which is 76. And osmium has 76. This one, again, if you look, radon has 86 plus 2 plus 11. Hello? Yes, I'm going to try to be given a test of everything this week too. I was thinking of trying to have the test tomorrow, because I have nothing else to do. And the homework and that are all like identical. So, you know, they can continue trying to work like Thursday and Friday on homework too. Yeah. So 86 plus 2 plus 11. that'd be 13 plus 86. So 99. 99 is istanium. So E6. You can also look at the last one. So this is your 4F. This is your 5F. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we see istanium is a 6. Note the best way of doing this is make sure you count the electrons. Counting the electrons is guaranteed to be right. As we saw, copper is not correct if you do off-ball roll because it likes to fill that half shell first. Anyway, from order, it's already in order. So from greatest is E, then D, then C, then B, then A. I should have put arrows. Alright, place an X on the blank configurations that are not correct. So, looking at the order, we should go 1S, 2S, 2P, 3S, 3P, 4S, and 3D. This should be a 3. You can see it right here. After 4S comes 3D. Another way of guaranteeing this is right, let's look at this. Let's look at all the 3s. So here's a 3, here's a 3, and here's a 3. They're all going to always be SPDF. So looking at this, we have 4S and then 4D. There was no 4P between it. 4P should come between 4S and 4D. So that's a good giveaway right here. We shouldn't do a 4D before we do a 4P. And we have to do a 3D somewhere after 3S and 3P. So looking at this one, we can see right here is a mistake. 3S, 3. The most that can go in S is a 2. There's another mistake too, and that is D. It should go 3P after the 3. I didn't count it wrong if you only circled one of them, but this has 2 mistakes. You should have circled both of these and both of these mistakes. So looking at the next one is in noble gas configuration. Let's look at the noble gases. The noble gases is helium for He, Ne is for neon, argon is Ar, krypton is Kr, xenon is Xe, and radon is Rn. These are all the noble gases. Ra is not a noble gas. Ra is radium. So what's wrong with this is this one as not a noble gas. Let's look at this one. This is full. That's partially full, but it's alright. That's the last one partially full. This is full. That's the correct order. This one's fine. This one. This is a noble gas configuration. However, you could either circle the whole thing or circle here. I count it right regardless. That's not the correct way of doing noble gas. If you wanted to do the noble gas configuration for xenon, then you look at the previous noble gas, Ar, and then you write the row. The row for xenon will be 5s2. Then remember that your F's go after, it doesn't matter. It goes after here. Here is where your F would go. But it doesn't matter. So then it would be 4D10 and then 5P6. This is the correct way of writing a noble configuration for xenon. You choose the previous noble gas. Noble gas configuration for bromine is, so bromine is number 35 on the right side. So 1s, 2s, 2p, 3s, 3p, and it should be in the 4p spot. So 3p, and 4s, and 3d, and then 4p. Bromine is the fifth one in it, so it'll be 5. All the rest of them will be full. And that's the correct one. So which of the following is in the same group? Group means column. So we're looking at P4. Everything, so 1, 2, 3, 4. Everything in here is P4. So really, you don't even have to look at the periodic table. Everything in the same group has a P4. This is the only one that has a P4, so this is in the same group. Noble gas configuration for potassium. Potassium is at the 4s, and previous noble gas, argon. Argon, and then 4s, and it's in the first spot. Circle the configurations with the same number of valence electrons. So these all have 1 valence. These have 2. These have 3. These have 4. These have 5. These have 6. These have 7. And the last one has 8. So basically everything in the same column. Everything in the same column has the same number of valence electrons. So we really only need to look at the last one. So P3, none of them have P3. D6, none of them have D6. But both of these have S2. So these two are in the same column and have the same number of valence electrons. They both have 2 valence electrons. Lastly, cation. A cation is just a positive ion. An anion is a negative ion. So we're looking at the ion version of gallium. Gallium is Ga. And everything in this group has a charge of +3. You want to lose these 3 electrons and become positive. And it says it right here, positive ion or cation. So we're looking at Ga3+. So we're going to remove 3 electrons. So initially it has 31. We're going to move 3, which would make it the same as argon. Kind of wrong. It's going to just have 31 minus 3. So that is 28. So we're going to make it have the same as nickel, I should say. So we're going to do 28 electrons. So 1s, 2s. So that gives it the same as nickel. 3s, 3p, then 4s, then 3d. That should be enough. So 2, 2. I did this wrong. Okay, so 1s, 2s, 2p, 3s, 3p, 4s, and 3d. So that'd be 2, that'd be 2, that'd be 6, that'd be 2, that'd be 6, that'd be 2. And same thing as nickel, so 1, 2, 3, 4, 5, 6, 7, 8. 8 here. Count up the electrons and make sure they equal 28. That's 10. That's 20. That's 20. So 10 plus 10 and 8 left is 28. Lastly, we get this one, the Lewis dot structures. So how many carbons or how many total electrons does neutral carbon have? That'd be 6. But valence electrons, again, everything in this column has 1, that column has 2, this column has 3, this column has 4. So it has 4 valence electrons. Chlorine. Chlorine has 17 in total. And everything in this column has 7. Idiom. Is 49. Idiom is in the boron group. So everything in there has 3 valence electrons. Calcium. Calcium is number 20. And it has 2 valence electrons. Selenium is 34. And has 6. Everything in here has 6. Antimony, Sb is number 51. Everything in here has 5. So Lewis dot structure. So Lewis dot structure for silicon. And when you do this, a lot of y'all, it's very hard to read. Because you put a dot above the I, and you put dots all next to it. Whenever you do it, space the dots out. So everything in this column has 4 valence electrons. What I do is kind of make the dots big to differentiate it. Sulfur is under oxygen. Oxygen has 6. So everything in that column has 6. So 1, 2, 3, 4, 5, 6. And note the order in which I did that. I went around clockwise doing 1 dot at a time. That's to show you the groups or pairs. Beryllium has only 2. Because it's in this column. Potassium.
Okay, teachers and students, I believe all the testers are done. The bells are back on, and with the next bell rings, we will be back on regular schedule.
I'm running out of time. So sodium, here's the main thing. What I think everyone got wrong. So for ions, your notation for ions, so sodium. So sodium is Na, and it has 1 valence electron. For ions, we write the symbol, Na, and when it becomes an ion, it's going to lose that 1 dot. So originally, it's like this, but when it becomes an ion, we remove the valence electron and we put its charge on the outside. Chlorine is normally Cl with one dot. But when it becomes an ion, we're going to add one electron to it. So we put brackets around it and gives it that 1 minus charge. I think that's the only thing y'all didn't do correctly on this puzzle. So potassium is in the first column, so it only has one valence electron. Boron is with 3 valence electrons, so we put 3 around it. Argon is a noble gas, so we're going to put 8 around it. So magnesium has 2, so we put 2 dots around it. Note how I'm putting the 2 dots. I do not put the 2 dots on the same side. I do not do this. I do not put 2 dots together. I should be counting it wrong if you put the 2 dots like this. So the number of pairs, when drawing correctly, is 0. So let's do sulfur. Sulfur has 6. So 1, 2, 3, 4, 5, 6. Now we see that when drawing correctly, going clockwise, there are 2 pairs on 2 sides. There's a pair on 2 sides. And there's 2 electron pairs. Helium, again going around like that, has 0. Carbon, again going clockwise around it, has 0. Germanium, number 32, it's in the carbon group, so it has 4. So 1, 2, 3, 4. No pairs. Neon, a noble gas other than helium. But helium's a noble gas, but it has most 2. So sulfur, and neon. Neon has 8. 1, 2, 3, 4, 5, 6, 7, 8. So 1 pair, 2 pair, 3 pair, 4 pair. So, on this one, you're supposed to look at gains versus loses electrons. Lithium has 1 valence electron. It wants to lose that 1 electron. Bromine has 7. Again, either wants to lose 7 or gain 1. They'd rather gain 1. Calcium has 2 valence electrons, so it either wants to lose 2 or gain 6. Easier to lose 2. Oxygen has 6 valence electrons, so it's either trying to get 8 or 0. So it's either going to lose all 6 or gain 2 to get 8. It's going to gain 2. Boron. Boron has 3 valence electrons. It would rather want to lose those 3. Argon is a noble gas, so neither. Or you could have put gain / lose 0. On number 5, indicate the charge an element will have when it loses or gains electrons. Become more stable. So aluminum has 3 valence electrons. So it either wants to lose 3 or gain 5 to get to 8. So it starts out with 3. It can either lose those 3 or it can add 5 to the 3 and make it have 8. Obviously, it's going to want to lose 3. And losing 3 is going to make it more positive. So the charge of +3. When it asks for charge, this is what it means, just a number. I didn't count wrong if you put aluminum 3 plus. But note, it's asking for charge only. So it's this. Phosphorus. Phosphorus has 5 valence electrons. 5 is closer to 8 than 0. So it's going to want to gain 3. Gaining 3 means that it's going to have a negative 3 charge. Gaining electrons make you more negative. Sulfur has 6 valence electrons. So it's going to want to gain 2. So gaining 2 make it have a negative charge, so negative 2. Fluorine has 7, so it wants to gain 1. So its charge is going to be -1. Same situation with iodine is 7, goes in the 7th column. So it wants to gain 1, gain charge -1. Neon is going to be 0. Neon is already stable. It already has 8 valence electrons, so it doesn't produce ions. So list the following elements. Ions indicated by their charge. I don't think I counted wrong if you just put the charge. But sodium,
Aaron Emerson, Zach Toothman, come by the office. Aaron Emerson, Zach Toothman.
sodium has 1 valence electron, so when it becomes an ion, it becomes Na+. It's going to lose that 1 valence electron and become an ion. You could have also put +1. I counted it both ways on this one. Calcium has 2 valence electrons, so when it becomes an ion, it becomes 2+. Chlorine has 7, so it's going to gain an electron and become 1-. Aluminum has 3, so it'll lose those 3 and become 3+. Sulfur has 6, so it's going to become, so sulfur has 6, so it'll gain 2 electrons to become full, so it'll be -2, or 2-. Boron has 3, same group as aluminum. Boron,
Zach Toothman, come by the office.
3+. Calcium, Lewis dot for the ion version of it, So we know that calcium is 2 plus. They're written over here. So it should have 2 dots next to it, but we removed those 2 dots to make it have a charge. Aluminum has a charge of 3 plus. Again, though, we removed those 3 electrons to give it that 3 plus charge, plus 3 charge. Boron, same for boron. We remove those electrons to give it 3 plus. Sulfur normally has 6 dots next to it. So this is the non-ion, or just a regular atom. But when it becomes an ion, we'll add 2 dots to it to make it have 2 negative charge. Ion notation, you put brackets around it and indicate the charge. So 4 protons and 4 electrons. 4 protons corresponds to beryllium. We're doing a Lewis dot for it. Since the same number of electrons and protons, it has no charge. So it has a valence electron of 2. So we put 2 dots. 36 protons corresponds to krypton. Krypton's a noble gas. This is the same number of electrons and protons. We'll have 8. 13 protons corresponds to aluminum. But it has 3 more positive charges than negative charges. So it's going to have a 3 plus charge. Normally, it's written like this with only 3 dots. But to give it this 3 plus charge, we had to remove the dots. Again, this is ion notation. 35 corresponds to bromine. Again, bromine normally has 7 dots around it, like this. So it normally has 7, but it has 1 more electron than it has protons. So we need to add an electron, and that makes it have a negative 1 charge. Sodium has 11 electrons. So the innermost, this is your 1s. So 1s has 2 electrons on it. Then we have our 2s and 2p. So 2 electrons there and 6 electrons there, giving us a total of 8. And then we have 3s1. So 1 electron in the 3, third energy level. When it becomes an ion, we're going to remove the electron. So this electron gets removed, giving it a full outer shell because this shell is scarce. Fluorine is 1s2, 2f2, and 2p5. So for the 1, it's 2. And then there's 1, 2 plus 5 is 7. 1, 2, 3, 4, 5, 6, 7. When it becomes an ion, we're going to add an electron. 1, 2, then we got 7 here. So when it becomes an ion, we'll add an electron. And now it has a full outer shell. So what do you notice about the difference between atom and its ion. The outermost shell has less than 8 electrons. More accurately, the outermost shell is not full, because remember there's a exception, helium. And ion has a full outer shell. Or has 8 on the outside. With the exclusion of the innermost energy level being full when it's 2. So last thing to remember, so let's look at the second energy level. An energy level is also called a shell. Subshells or sublevels are the entire blocks, and orbitals are the individual blocks. So going back to this square right here, just this square, is called an orbital. This whole block is called a subshell. And if I look at, so this is also a subshell and an orbital at the same time. This whole thing is a subshell and has 3 orbitals. So if I look at this, this, and this, all 3 of these make up the shell. And the shell is the same thing as energy level. So this shell has 3 subshells and 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals. So a subshell is an energy level. A subshell is the same thing as a sublevel. And I believe that's everything you need to know about the test. looking at the actual test, there is less emphasis on ions. There's actually only 4 questions, and they asking you to name the charge only. We have 3 questions where you have to do the full electron configuration. 3 questions where I ask you about the abbreviated noble gas configuration. 4 questions which has a table. The 4 questions were total electrons, total valence electrons, and then write the Lewis dot structure art. 4 questions asking about the ion. 3 questions where I ask you which rule does it break, off-ball, Hund, or poly, and also explain why it's wrong, and write none if the configuration is correct. You also need to know about max number of electrons that can go into a sublevel. So, for example, in the sublevel 2s, or I should say the sublevel S. So sublevel S can only have 2, sublevel E can have 6, sublevel D can have 10, and 14 for F. So we can see in the second energy level, at most only 8 electrons can go in it. You could do the same thing for 3, but looking at just 3s, how many can go in that? You can do the same thing for 4. So 4 is composed of a 4s, and then a 4p, a 4d, and then a 4f. So 2 can go in here, 6 can go in here, 10 can go in here, and F can have 14. So 6 and 14 is 20, 20 plus 10 is 30, and 30 plus 2 is 32. So a total of 32 electrons can go into the work energy level. And that'll be it for the test.